The next important block of a PLL is the VCO, or the voltage control oscillator. So as the name suggests, it is an oscillator which is controlled by the voltage. So it is something like this. If I just draw the block diagram, it is on one side the input will be a voltage. Okay, so let's call it as the control voltage which controls the VCO, Vcont. Okay, this is my VCO, and on the other side it will spit out an oscillation frequency, sine wave or a square wave, right, of a frequency like f out, right, whose frequency or the frequency of the time period is 1 by f out. Frequency is f out, or we can say it as omega out. Okay, so for a particular voltage, it is going to spit out a particular frequency. So the question is, why do we require a voltage controlled oscillator in a PLL? So if you go back to the blog that we have discussed here, right? So basically what happens here is what we have seen in the last lecture is that we try to whatever the frequency that is spitting out, which is n times of the f in, the f out is n times of f in, it is divided by the divider, and finally we try to compare with the input frequency. So the output frequency, which is n times f in, has to be generated by some by some oscillator. So here we use a VCO. So this VCO is going to generate that n times f in frequency. Okay, so the VCO here is going to generate the frequency which is n times the f in, and of course we have the control voltage here. Okay, so this is going to generate the n times f in frequency, okay, for a particular control voltage. Now the question arises is, why at all then we need a PLL, right? We can just identify the voltage, okay? We can identify the voltage for which the VCO is generating that particular frequency, and that's it, right? So this is a question. Of course, this is a very valid question. I'll come back to this question after discussing a little bit about the characteristics of the VCO. Okay. So let's go back and discuss the characteristics of the VCO. Okay. So what is a VCO? VCO is, as mentioned, that it generates a frequency, and it has a direct relation with the control voltage, and it is governed by the equation, the f out or the omega out. I can write in terms of the f out, or I can write in terms of the omega. So we'll write in terms of omega. Okay, so is given by omega naught plus a constant which is called the KVCO and into the control voltage. Okay, so this is the equation of the equation of the VCO, that the output frequency that it is generating is equal to, I have some constant frequency omega naught plus this plus this KVCO into the control voltage that I am applying. So if I try to draw the graph of this equation, it's a very simple linear equation, and it looks like something like this, right? So my x-axis is the input, basically this is the control voltage Vcont, okay, and my y-axis is the output frequency that is spitting out, the frequency basically, okay. And if I draw the expression of this one, it is something like this, okay. So at when my control voltage is 0, it starts with a omega naught, okay. Let's see this different color pen. So omega naught is the frequency when my V control is 0, and of course maybe at some control voltage of let's call it as V1. It generates a frequency of omega 1, and maybe at some other control voltage, P2, it generates a frequency omega 2. Okay, and maybe let's maybe in the actual sense, what happens is the VCO is limited by a range. Okay, so it cannot of course generate any frequency. It is like in real life, of course ideally it is supposed to, but in real life it is restricted to a range, right? Restricted to a range of omega 2 to omega 1, and the control voltage varies from V2 to V1. Okay, so it may not even reach to omega naught. Okay, so or even if it reach it may be just an imaginary line, so actual in the real life the characteristic may come down something like this. So the linear region is only from here to here. Okay, so of course we'll discuss about this linearity and all later on when we come to the actual implementation. But what we mean here is that the actual, the region may be just from omega 1 to omega 2, and we can say that this may be, I should say that this may be a, imaginary line. It is intersecting the y-axis at omega naught. Okay, so this is the characteristics of my VCO. Okay, and of course the KVCO is nothing but the slope of this line. Okay, the slope of this line is the KVCO. That this is a constant, and this just like we had the KPD, which characterized the phase detector. Similarly, the slope of this line defines the characteristics of the VCO. Okay, so the slope is the KVCO, and of course we know the unit, right? The unit here in this case, the unit of the KVCO will be hertz per volt, or radians per second per volt. Okay, so let me write it down. So unit of KVCO is maybe hertz per second, or if you're representing in omega, it is radians per second per volt. Basically what it means is that how much frequency it is generating for a particular control voltage. So this is what is the VCO, the KVCO. So I am varying my control voltage, and correspondingly it is spitting out different frequencies, right? Higher my control voltage, higher is the frequency. Lower is my control voltage, lower is the frequency, and there is a linear relationship. Okay, and of course because it cannot generate infinite frequencies, it is limited in terms of the input voltage as well as the output frequency. So this range is called the tuning range of the VCO. So tuning range of the VCO is omega 2 minus omega 1. So this is the range, right? This is the band of the frequencies that it can generate. Okay, so this is the VCO. Okay, so and this is what we will be inserting in a PLL. And if I want, of course my output frequency, which is n times f in, should be in these tuning rates. It cannot be outside, right? So we have to make sure that n times f in should come here, and preferably in the mid region. Okay, so n times f in or n times omega in, right? If we either it can be in the hertz, which we denote by f, or in omega, which will be in the radians per second. Okay, so what it means is that it should lie somewhere in the middle, right? So this will be the n times omega in, or n times f in. Sorry, you should use a capital letter here. N times omega in. Okay, the input frequency, or n times f in. So this should be the and correspondingly, of course, I'll get a voltage. Okay, correspondingly Correspondingly, we'll get a voltage, and this will spit out the n times f in or n times omega in. So it is going to spit out that that particular voltage for omega in or f in, right? It's just the yeah. So we know that it's just a difference of 2 pi. Okay, so yeah, so we need to find out that particular voltage. So one may ask, like one may tell this question, look, why do we need all this complicated structure of this loop and all, why PD and all? How I can just figure out that particular voltage and it will just oscillate at n times omega in. So so it's pretty simple, right? I'll just find out this voltage, and that particular voltage, very nice voltage Vx, so where it will just spit out n times omega in, and there is no requirement of PLL. Okay, so this doesn't happen like this. Real world is not very simple, because the thing is that these characteristics may have a variation, right? So I may have these kind of characteristics when I'm doing simulation, but when we actually do the fabrication of the VCO, so this can have some different slopes, little bit difference in the slope, or this characteristic may vary, right? Little bit may vary, with change in the temperature, right? We know the mobility changes of the MOSFETs, because we are going to ultimately implement the VCO with the MOSFETs, and the MOSFETs will have a variation of mu, right? The mu varies, right? So with this variation, there can be a difference in the characteristics of the VCO. So that means this voltage will be different, so with the temperature, or it can happen that there can be a noise, right? Noise in the voltages itself, right? Noise in the I should say that supply line and all, because of which all the voltages are not constant. So even though we are generating a voltage Vx, but there may be some noise coupling, and it may run around, and then it can deviate from n times omega in, because we just want precisely n times omega in, because the requirements, the frequency requirement is very, very strict. Okay, and the other thing is that it is same like telling that why do we have to go for a feedback circuit in an amplifier circuit, right? Something like this, if we can design an amplifier of a specific gain, right? So so the same reason also applies here. So when we design a gain amplifier of gain A, right? So with a change in the mobility and all, or even with a change in the resistance and all, so it is possible that the gain will change, right? So now the question mark comes is, what if, okay, the ratio is now dependent on the, the ratio is very much dependent on the ratio of the resistance. So what if the resistance also changes? Yes, the resistance changes. In fact, the resistance inside the IC very easily changed by plus minus 20%. Okay, if you have done any design on cadence and all, you can see that with the process variation, right, from fast corner to slow corner, the resistance easily changed by 20%. But the good thing about the IC design is that the matching is very easy, right? If I fabricate a resistance here and another resistance here, and if the matching between these two can be brought lesser than I should say that 1% very easily. So in the sense that if this also varies by plus minus 20%, right, plus minus 20%, this also will vary by same amount plus minus 20%, because both of them are fabricated using the same process and in the same environment, and because of which the matching of these two becomes very easy. That's why we go for feedback circuits, because here we are more focused on the ratio. So if one goes by above by 20%, the other also goes by 20%. That's why we go for a feedback circuit, right? So so the same question is like, although I have a good gain amplifier, why can't I just design an amplifier of specific gain and get the amplifier? So same concept applies here in the PLL, that yes, I cannot design a VCO of a particular frequency, because the frequency itself is going to change. That's why I need a feedback system to control, right, to control the voltage such that it spit out exactly n times f in or n times omega in. Okay, so yeah, so yes, so let's come back to the discussion of the VCO. Okay, so this is why we need a VCO in a PLL system. Okay, so discussing more about the VCO. So to look into the VCO, we can say that the output of the VCO, if I just try to write down the exact expression of the output of the VCO, can be something like this, like that. So it, yeah. So if I have some, like, if I have suppose I have an oscillator and it is oscillating at sine, omega t. Okay, so then we can represent this as Vm sine pi t. Okay, so or we can say that this is the phase. Okay, so phase, and phase is nothing but the omega t. So I should say that the Razavi has very nicely explained this concept in the book. So what it means is that how to see the phase, right? How to see the phase is very important when we say the phase log loop, right? So if I see this t and if I see the phi t, okay, so what I'm going to get is I'm going to get something like a straight line. Okay, so with every increase in the time, right, my phi is going to, uh, the phi is going to increase, right? So it is going to become pi, this is going to become 2 pi, and this is going to become 3 pi. Okay, so with the time increase and the slope, by which it is increasing, of course, it's by the omega. Slope is omega. Okay, and if you see exactly how the V naught is looking with t, V naught t, it is, of course, it's just a simple whatever we have learned in the maths or in the class 2. It's not a big deal, but this is how you should visualize the thing. So I have a sine wave that is V naught is generating. Okay, this is the corresponding 2 pi something, right? So V naught it is generating, this is the waveform that is generated by the VCO. Of course, here I've just mentioned the frequency omega out, omega, but actually the actual waveform, the equation of this actual waveform is this one is the V naught t, and it is omega. Okay, so now if we see this phi t, right? So the definition of the frequency or the omega, okay, is nothing but the frequency in radians, right? Frequency in radians, which is nothing but the omega, is defined by the slope of this line, or slope, or it is just seeing how fast my phase is changing. Okay, so this is d pi t by dt. Okay, so if I see that, because actually what we are going to see that here it is very linearly changing, right? But in some cases it's not going to change linearly, it's going to have different curves. Okay, so then to know my frequency, I should just do the I should say that I should d pi t by dt. Okay, or it can be for simplicity it's sometimes represented by just by d phi by dt. The t is dropped, assuming that this phi is having a variation in the with time. Okay, so these equations may look very simple, but I should say that this is the basis of the PLL. Okay, so this is the basis of the phase log loop. Okay, so yeah, so if this is the basis, let's try to understand more in details. Okay, so yeah, so if we go back and if we try to bring if we just copy and bring this circuit again. Okay, just copy and bring this back and paste it there. So I have my input here, and I have my F in and omega in, and of course I have my PD and I have my VCO. Okay, so I have my VCO here. Okay, and of course this PD is also trying to generate a voltage. Okay, and but this voltage, we have seen that after the PD, we know that it is like a ones and zeros, like it is like it's a digital bit, right, after drawing, right? So we cannot apply this one directly at the VCO, because what will happen is, if I'm just applying a digital bits information, so we can see that this will just be jumping around and it will spit out different frequencies. Okay, so what we need is that we need to have a very smooth stable voltage here, or we should say that the average value of this voltage, and we should feed to the VCO. So the simplest averaging way to do the averaging is using a low pass filter. Okay, so we can use a simple low pass filter, maybe as simple as the first order low pass filter. Okay, and with a simple RC circuit, and we can feed the output of the PD to the VCO. Okay, so we are going to feed because it's going to have lot of jumping digital ones and zeros. So we are going to have a low pass filter, and the output of the low pass filter is going to be fed to the input of the VCO. So the main purpose of the low pass filter is averaging. Okay? So because we ultimately wanted to give the average value of the output of the PD to the VCO, as we have discussed, right? So even the PD, right? When we say KPD, we are focusing on the average. So how we are doing the averaging in the practical sense? Using a low pass filter. Okay. Yeah. So now this is the complete picture of a VCO. Okay. So basically what it is trying to do is that the PD is trying to detect, like, whatever the frequency this is generating. We are dividing it by N, and we are telling that, look, spit out a voltage such that this VCO produces N times F. If it is deviating, try to lock in, right, with a feedback system. Okay, that we'll discuss more. Okay, but here so this is the entire loop that is happening. This is a feedback system, so this is a negative feedback system. Okay, so there should be a negative loop, right? So which means that if the phase error is increasing, then so accordingly the control voltage should be set such that the phase error reduces. So that part we need to see. Okay, so otherwise, if it is a positive feedback system, it's not going to work. Okay, so what it means is that, see, now what the input is has an omega in or F in. So just write only one of them. Okay, so with an omega in, and of course we have the phi in. Okay, phi in corresponds to the phase. Okay, and omega in is the input. Okay, and it is giving an n times omega out, or n times omega in, or let's call it as omega out or phi out. Okay, omega out or n times omega in. Omega out is equal to n times omega in, and it will have a phase, right? It has a phase which we will call it as phi out. Okay, so the definition of the phase and the frequency that we have seen in the last here. Okay, so this is what exactly the definition of the omega and the phase, right? So what I mean is that there's a like phase, right? Phase that is that we are going to put this phase in the sine, right? Sine equation, and of course we are having a phase out. Okay, so to simplify the stuff, we'll first analyze the case when n is equal to 1, and then we can go to those cases where n is 2 or 4 or 8, like that. So let's consider that I'm just trying to generate by the VCO the same frequency as the input, right? So what I want is that I want to have omega out is equal to omega in. Okay, so suppose if we can find out a condition, or if we can make this such that these two, the difference between them is always constant, phi out minus phi in is equal to constant, then I can say the PLL is locked, or we have achieved whatever we want. Why? Because if I do the differentiation, what I'm going to get is d phi out by dt minus d phi in by dt is equal to 0, and this is, we know that this is omega out, and we know that this is omega in is equal to 0, implies omega out is equal to omega in. That means we have achieved whatever we wanted. So this can be achieved only if we can say that the phase error, basically the phase of this one and this one is the difference is constant. There may be a phase difference, but we can say that the frequency is the same. It is quite simple to understand, right? If I have some sine wave, something like this, right? So if I have another sine wave, right, and if the phase difference between them is constant, I can say that the frequency of these two are the same, right? So it is not necessary to be a particular, like, phase difference should be 0. It can have a phase difference, but that particular phase difference should be constant. So that is the basic concept of the PLL, that we want to make the phase of these two the same, right? So one may ask, like, to get this one, why we have not used a FD, or why we have not used a frequency detector? Okay, the reason is very simple. Like what happens is, when we use a frequency detector, right, then there can be an issue on the offset, right? So the question is, it's a very important question, that why we don't say FLL, right? Frequency lock loop. Why we don't say, like, why we don't compare the two frequencies and tell the VCO to generate that particular frequency? The reason is very simple, because see, when we are designing some op-amp, something like this, right, maybe a source follower op-amp, let's give an example of this op-amp. So this is very nicely explained in the Razavi book as well. So see, what happens is, if I am a voltage follower, so ideally what I'm supposed to get is V in and V out will be same. So I'm supposed to get this is equal to V in, but in actual cases we may not get, because of the offset, right? There may be because of the device variations and all, there will be an offset, and we only can say that V out is approximately equal to V in. So there may be a few millivolt offset. Okay, so, but of course this is acceptable in case of the voltage, right? But in case of the frequency, if we try to compare it to frequency, right, when we are comparing, and if there's an offset, right, if there is an offset, if because of comparison, because of the device problematic, if there is a difference in the comparison in the, right, so that's going to give an error, right? And that's going to make the same whole system error. But here, if we are measuring, if we are trying to see the difference between the two phases, and you can see that even if there is a error, right, in the comparison of the two, but if, as long as the phi out minus phi in is constant, then we know that the omega are the same, right, the frequency itself. So that's why this concept of the phase locking is used instead of frequency locking. Okay, so this is very important that we need to understand, and this question, why it's not called FLL and why it's called PLL, that will come, that's a very basic or common question that arises. Okay, so now let us try to understand the PLL in a lock condition. So suppose the input frequency is omega in, and the output frequency is omega out. Okay, and maybe let's omega in is equal to maybe omega 1, and we want in a lock condition that omega out should also be equal to omega 1, and of course let's call this as phi in and phi out. Okay. Okay, so this is the scenario. So let's try to analyze what is happening in the log condition. So if you try to again replot the characteristics of the VCO, it is something like this. So I have my V control voltage, V cont, and this is my omega out, and we have these characteristics, and currently our PLL is locked, and the output frequency, the splitting out, is omega out is equal to omega 1, and the corresponding voltage, maybe let's call this V1. So V1 is required for the VCO to oscillate at a frequency of omega 1. Okay, so yeah, so of course in log condition, omega in is equal to omega out is equal to omega 1. Okay, so now if you see the characteristics of the phase detector as well, so the BPD, the average value of the BPD, so this is basically the output of the BPD, and the phase difference, which is basically the phi out minus phi in. So it should spit out that much amount of the phase, maybe let's call it as the BPD. The average value should be equal to V1. Okay, average value after low pass filtering should be V1, and maybe just call it as phi naught, where phi naught is the phase difference between phi in and phi out. So what it means is that my phi in and phi out should have a phase difference of phi naught such that the average value is V1, and V1, and once the V control is V1, then the frequency the VCO will be oscillating will be at omega 1. Let's try to see this one again graphically as well with the waveforms. So I'm using the previous this waveform that we have drawn before. So this is my phi in, this is my phi out. Okay, so the the input phase and the output phase with a omega frequency of omega in, or now it's equal to omega 1, and this omega out. Okay, and of course this is the my BPD. Okay, and there is a finite phase difference of phi naught. Okay, so there is a finite phase difference of phi naught now, so, and which is required to produce a voltage of V1. So I have a phase difference now of some other color of phi naught. Okay, and of course this is producing a control voltage. Okay, so V which is V cont, and this is generating a control voltage where the average value of this one in the log condition. So after low pass filtering, we can see maybe some small ripples here. Okay, because of this one, and because of this one also there will be some ripples. Some ripples will be there. Okay. Something like this. And the average value of this one, this is the average value is, this is equal to V1. Okay, the average value of this one after doing the filtering, this is equal to V1. So this is the V control voltage. So this is how a PLL looks in a log condition. Okay, so basically I need to, in this case, I need to have a finite phase difference of phi naught, and this ultimately will give a finite, I should say that finite voltage V1, and because of which it will be oscillating at a frequency omega 1. Okay, so this is a modulator block. Okay, if you just click here, so this is a spice model, which is a modulator. okay. And this can be used as a, this can be used as a VCO. Of course, it's just an FM generator. That means depending upon the voltage, it's going to spit out a particular frequency. Okay, and its characteristics, the KVCO and everything is defined by this one. Okay, we'll learn about more about this one. So before that, what we'll try to do is we'll try to input a voltage here, because we are not using it as an AM modulator, so we are grounding this part. Okay, so let's get a voltage source. Okay, okay, and then let's get a pin here, maybe VCO or V out, simple. This will be the output here. It's the output, and ground. Okay, so I'll be sharing these files so you can do experimentation yourself. Where's okay, fine. So now let's give maybe some voltage, maybe just give maybe 0.5 volt. Okay, so this is the voltage that I'm applying, and it's supposed to spit out a particular frequency. So what frequency it's going to spit out is defined by this one. So there are two parameters. This is called the frequency high and the frequency low. L stands for low and H stands for high. Okay, and it is generating a high means it's generating a frequency of 1.5 megahertz, e power 6 is megahertz, and 0.5 again megahertz. Okay, so this two is defined by if you see the, let's go here. Okay, so these two are these 2 points. So this basically are the 2 points. So here there's something like this. If I have a VCO characteristics, okay, so this is the point of, this point is basically the FREQH, and this point is FREQL. Okay, and if you see the V control, this is 0 and this one is 1. Okay, so this one is basically this one, is the, and of course this is the frequency F out in hertz. Okay, F out in hertz. So this is the characteristics which is given by these two parameters. Okay, so now from this we can easily find out the KVCO. In this case it is FREQH is 1.5 megahertz and it is 0.5 megahertz. So if you see here, so this, in this case it is, let's write down the number for this example, you can always edit it. So this is 1.5 megahertz and this is at 0 volt. When we control 0 volt, this is 0.5 megahertz. Okay, so of course we can do a simple calculation, simple maths and all, and we can find out what is the frequency at 0.5 volt, and we can find out the KVCO. KVCO will be in this case, VCO will be in this case, and this is 1.5 minus 0.5 by this X spacing is 1 volt. Okay, so the KVCO is 1 megahertz per volt. Okay, so of course then at 0.5 volt, okay, we can easily find out that this is going to spit out a frequency of 1 megahertz. Okay, this is in mid. This we can do it by, so this we can easily find out as 1.5 plus 0.5 by 2. Okay, so in this way we can find out the midpoint. Okay, So because we are giving an input voltage of 0.5, so it is supposed to give a frequency of 1 megahertz. Okay, so let's do the simulation and see. So I will go for a spice directive transient simulation. So again, right click, have made it analysis command. So transient, so because it's a 1 megahertz, maybe to see maybe 3 cycles we can give 3 micron. Okay, okay, and just put it, run it, then click here, and you can see that this is a very nice 1 megahertz, because if you see here the time axis is when it is 00, you can see that or you can just and get the cursor point. You can just click there and get a cursor point, and we can see here that the frequency here corresponding to this one, when it is half, right, half 0.5, because its waveform is going from 0 to 1, so we can see that the frequency is exactly 1 megahertz. And of course we can change the voltage. If you want, we can change the voltage and see that if it is 1 volt, it is giving a frequency of 1.5. You can measure yourself, it's giving a frequency of 1.5 megahertz. And of course, because this is an ideal VCO, this goes on and on. I mean, it can go, it can be extended long like that. So even if you give a 2 volt, you can estimate, because you know the slope and you know the y-intercept. From there we can find out the frequency that the VCO will be oscillating. Okay, in the next lecture we'll try to understand the loop dynamics of the PLL. Thank you.